right, thank you. So I'm going to try and cover a lot of territory. I'll go a little bit fast to get through it in my allotted time. Forgive me. I hope the package is going to be very helpful for the things that you can refer back to. I'll mention one thing in the package. I believe you have some data that I won't be showing slides on for new values for cities. I'm going to focus in the talk just on the Pacific Northwest. But the package does contain numbers for other parts of the United States. I'd like to acknowledge also my co-authors on this presentation, Dr. Nicolas Luco, who will speak next, and Professor Andrew Whittaker. These are two of the many key people who have contributed to the development of these new code ground motions. And also I need to mention the various agencies that have funded this, including USGS, and you can see that their involvement already, but also FEMA, which really supports the NEHRP provisions process, and the Building Seismic Safety Council, which actually implements that process. So there's a lot of agencies and a lot of groups and a lot of folks that have gone into this work. I will spend some time on the background of building seismic codes. Where do they come from? How do they get developed? Actually, we were asked very much to do this so that the audience would understand that this is a very, let's get rid of that. End show, next, previous. So how do you get rid of that, Gabe? Click, okay. Click, oh, good, thank you. We want to talk a little bit about where all this stuff comes from, and I'll talk a little bit about the new ground motion criteria that was developed by what we call Project 07, which is one of the groups within this massive process of developing code information. I'll hit on the key concepts that came out of Project 07 from an engineering perspective, including risk-targeted ground motions, use of a different measure of ground motion intensity, and a different way of looking at deterministic ground motions, a little bit different from what's been in the previous codes. And I will close with some example values of new numbers for 34 cities throughout the United States. And as I said, I'll focus on the Pacific Northwest for this talk. Codes are all about life safety. 4,000 years ago, we didn't have all this good science and engineering, but Hammurabi knew that he wanted things to be safe. He had a different way of achieving that safety, basically by putting the monkey on the builder's back. But we still think that way in terms of life safety. But we don't think just in terms of life safety. Actually, we are thinking a little bit beyond that. Life safety is still the primary point of view. That is, if you look into the commentary of these documents that I'll be just discussing, they say very clearly our primary purpose is to avoid serious injury and life loss. We also want to keep critical facilities open. We also would like to minimize damage, but the primary way we do that is to keep the building standing in rare events. And that's the focus. Now, the words you see here are the new commentary of the NEHRP provisions, and these words were wordsmithed over and over and over. And there's no, by the way, there's no 100% agreement on this. We try to get what we think we're doing in codes down on paper, but it's amazing to watch how these things morph as people say, well, what about this? What about that? But 10 again, life safety is the primary focus. In the building code process, when you go to a building department and you say, I'm going to do something, what's the rules? That's a code, that's a law. It's where the building department, the jurisdiction of that authority, it could be a state jurisdiction, local jurisdiction, they have adopted some rules for building buildings and designing and constructing buildings. They can't develop those rules from scratch, so they turn to what we call model building codes. And the major model building codes are done on a national level, and they include such things as the 2006 IBC, that's the current model building code, International Building Code. Used to be the UBC, now it's the IBC. Some years ago, they got in a little turf war with the fire guys, the NFPA, and the NFPA came out with their own version of a building code. So there's actually two national building codes, but the IBC is the dominant building code. A application of this in a code sense is on regional basis, where a jurisdiction, like in California, says, I'm going to take one of these model building codes, I'm going to tweak it. I'm going to add things to it the way I like, and then I'll make it my code. So we have regional codes such as the California Building Code, where I'm from, which is a derivative of a model building code plus some stuff that the state wants to add on their own. Major cities will do this: Los Angeles, Seattle, San Francisco. They will also have their own building codes where they take a model building code and before they adopt it, do some tweaking. Now, model building codes do not come out of thin air. They have to come from somewhere where people have sat down and done some homework to put these ideas together. And therefore, there are what we call source documents to model building codes. And the major source documents on the national level are two: the NEHRP provisions, which has been around since the late 70s, in effect since the late 70s and early 80s, and ASCE 7, which is a standard. Now, ASCE 7 includes both earthquake and other loads, so it's not just earthquake. And these documents are put together by groups of people, various committees, and really create the ideas, if you will, that then go into the model building code, which then can be adopted by authorities. And in a traditional sense, one of the major documents, and the document, if you go back 50 years, was the SEOC Blue Book. Where I'm from, the Structural Engineers of California would produce this document, which was used directly in the old UBC. And it's now passed on, and these NEHRP provisions in ASCE 7 have taken over where the Blue Book used to be. But again, that's a lot of the ideas that you'll see in the current codes can be traced back to the original work of the SEOC Blue Book. Cartooning this story, if you will, if we look back, say, 10, 20 years, we would see that there was the NEHRP provisions in the yellow, which fed into, and is still feeding into ASCE 7, the seismic provisions of ASCE 7. And then in parallel, there was this SEOC Blue Book out in California and western US, and they were feeding into regional model building codes. So 10, 20 years ago, we had regional model building codes: the Uniform Building Code in the western US, the Standard Building Code in the south, and the BOCA, or National Code, in the northeast. And they thought, after a while, that's kind of stupid. We need to get together and have one code for the United States. We'll call it the International Building Code, which really bothers people who don't live in the United States and wonder why we get to call it international, but they did. So we now have one code for the whole United States. As I said, there's a competing code, but the main code is the International Building Code, and it is being fed by the source document, the NEHRP provisions, or has been in the past fed by the NEHRP provisions, but now in the future, the model building codes, whether they be International Building Code or the NFPA or the California Regional Building Codes, they will be looking to ASCE 7. And instead of taking the words out of 7 and just slamming into the code, they're going to actually say, they're going to reference 7, ASCE 7, because it's a standard. And the idea is that instead of these model building codes can just reference the standard, and then you can buy two documents and everybody has to pay more money. But the ASCE 7 is still heavily linked with the NEHRP provisions. And so at this time, what you see in NEHRP and what you see in ASCE 7 is really much the same thing. And in fact, the way the process is working right now is that the real work on developing new ideas is done first and put into the NEHRP provisions. And if it flies in that process, if it sticks, then it's put forward into ASCE 7. And if it sticks, then it's put forward into the International Building Code. And so the first step in the process is for the Building Seismic Safety Council, who's in charge of the NEHRP provisions, and their committee, known as the Provisions Update Committee. Catchy name, Provisions Update Committee, because you update it every 3-5 years. That's where that real work is done, and the group I'm going to talk about is part of the Provisions Update Committee. The Seismic Design Procedures Reassessment Group was a subset formed specifically to look at this ground motion criteria. So that was where the work began about 3-4 years ago. We developed our ideas about 2 years ago, brought them forward to the PUC, and eventually got them into the NEHRP process. And toward the end of that process, then these ideas, these new ground motions were brought forward to ASCE 7. That's through the ASCE Structural Engineering Institute, which is in charge of this particular document. And they have a special task group for seismic, so that committee had to stew on these same ideas, and they just recently passed them. And now that they're passed, they're now being, as we speak, brought forward to the International Code Council, which is in charge of the IBC, and they'll have public hearings at the end of this year and early next year. And if all goes well, this thing that started 4 years ago will end up in the 2012 IBC. So that's just a long and torturous process. And those of us that have to be in charge of this, you get waterboarded a couple times here for sure. I mean, it's grueling. Let me talk a little bit about the Seismic Design Procedures Reassessment Group. That's where these real ideas came about. First, I have to say, many of the new ideas are new from Project 97. We had this project 10 years ago to take a look at how to get away from zones and get into contours and do a lot of stuff. So Project 07 was really a revisiting of the Project 97 work with the idea of folding in all that new hazard information that Mark was talking about, as well as seeing if we had other things that we should be doing to improve our thinking on the subject. Now, to do this, a group is formed to work through it, and this is the members of the group. I chaired the group. You'll see C.B. Krause, who's going to speak later, is on the group, as is Nico. But the idea of forming the group is to have a mixture, and I wanted to underline this because we get accused of this a lot. The underlying names are people from California. See, there's only 3 people from California, okay? And in fact, there's a nice mixture between East and West because it turns out most of the people are not in the Western U.S. They're all from all over. And also a mixture of scientists and earth scientists and engineers. So in the green, we have the, if you can see the green kind of, the greenish, that's more of the earth scientist, engineering seismologist, ground motion expert, and then the red is more of the practicing structural engineer. So the idea is mix the East, the West, get some scientists, get some engineers, bring them all together. And the people that don't have anything like myself, that's the jack of all trades people that show up for this thing. So we were tasked with 3 major things to take a look at in this revisiting of the last cycle. First, was the level of uniform hazard, which is 2% in 50 years, which we're now in the last cycle using to characterize probabilistic ground motions, was that really the right way of going? There's nothing sacred about 2% in 50 years. We made it up in about 15 minutes, okay? Nothing sacred about it. But boy, once it's in there, it becomes sacred. Are we using the right ground motion intensity parameter? I'll explain more about that later. And have we got the right shape to the spectrum that we use in the codes? We did not take any action on that particular item. We stuck with the same code shape that we've been using. We brought forward these ideas, as I said, about 3 years ago. They gelled into a single proposal, which has got a funny name. Doesn't matter. It's done. And it was just actually finally approved in March of 2009. In parallel, we brought a similar proposal forward to ASCE 7, and it was just passed in July of 2009. But I find that nothing is actually ever done until they print it. And in fact, since the times I made these slides all of, 3 or 4 weeks ago, since the time I made the slides, somebody has had a meeting and decided to slightly change the name. So, in fact, nothing is done until, I guess, the committee sings. Anyway, in all likelihood, it will go ahead and it will be in the 2012 IBC, and that's in the works, as I said earlier. Okay, key components. What are we talking about changing? If you're familiar with the code, and I'm talking now about ASCE 7, although the NEHRP provisions has exactly the same numbering system, so it doesn't matter whether I'm talking about the NEHRP provisions or ASCE 7. They're very similar formats on purpose. But if you look into the section that describes the loads for designing buildings, it's Chapter 11, Section 11.4. So these seismic coefficients that come from the maps are in Section 11.4, and the maps that they're looking at is in a chapter called 22. But there's another very important chapter in the document, which CB is probably going to spend some time on, and that's Chapter 21. That's where you do site-specific analysis. That's the rules for site-specific analysis. And I'm here to say that the rules we use to get the coefficients that go into Chapter 11 are the same rules that you will see or should see in Chapter 21 to the degree that we are able to describe them in a consistent manner. They should be the same. Most importantly, the new ground motions incorporate the new science from the USGS, which Mark has talked about. And then it has these 3 technical improvements, including the risk, targeted ground motions, the direction of ground motions, and for near fault in the deterministic region, a little more clarity on what percentile to use. I'll cover those a little more in a minute. If you were to look at ASCE 7 and the NEHRP provisions, and I'm talking about the new ASCE 7, so it's ASCE 710, and the 2009 NEHRP provisions, are there any differences? And the first answer is absolutely none technically. The coefficient that goes into the formula for designing a building, the spectrum you get from a site-specific analysis, it should be the same. However, there's a couple of nomenclature differences and some structure differences in Chapter 11, which have been lessened to some degree since this change. This MCE stands for maximum considered earthquake. It is now called in both documents MCE sub R. You can squint and just forget about the R. It's the MCE. It's the big earthquake. In my slides, pretend I have a little R down there next to the MCE now, because that was added since I did the slides. But that's not the difference that may be of interest. If you are interested in understanding how the deterministic and probabilistic stuff is put together, then you'd want to be looking at the NEHRP provisions in Chapter 11, because they have formulas breaking it into pieces the same way you do it when you do a site-specific analysis. In ASCE 7, we said that's unnecessary. Most users just don't care. Let's put all the maps into one map and just reference it and use it directly. So if you want it easy to use, ASCE 7, but if you want a little more on the pieces, you might go into the NEHRP provisions. Otherwise, but at the end of the day, the seismic coefficient is the same either way. Okay, ground motion characterization, a little background. In the purest form, of course, ground motion is a wiggle. Could be an acceleration, velocity, or displacement trace. We would use such wiggles perhaps in time history analysis, but that's not the most common way we design buildings. In fact, that's a very rare way we design buildings. We design buildings with some coefficient that somehow represents that ground motion. And to do that, we transform the ground motion into a response spectrum, which has got little zigs and zags and peaks and valleys. But we know that if we look at a bunch of them, they have trends, and those trends lead us to an idea of having a very simple, smooth, generic shape. And the coefficients are essentially defining the domains of that shape. And this is what the code shape looks like. It has an acceleration domain. I know for many of you this is not new stuff. Acceleration domain controlled by one coefficient, a velocity domain. It even has a displacement domain for very, very long period structures we're not going to worry about much. And these coefficients, the spectral acceleration used for design at short periods, S sub ds, is the acceleration domain coefficient. The coefficient S, spectral acceleration used for design at 1 second, which would then be divided by t to get it at other periods, is again the other coefficient that define the spectra. And then there's some rules about how to get the transition periods between one domain and another. But what is important is that these design coefficients that go into the base shear formula are 2/3 of the MCE. When I'm talking about an MCE, we take 2/3 for design. But we're not done there. People say, why do you take 2/3? You've changed the return period, all that good stuff. Oh, if that were only true. Because after we take 2/3, then we divide by R before we design the building. Now, R is a factor that accounts for inelastic response and displacement, inelastic displacement capacity and ductility and damping and all sorts of stuff that we study other ways. But that number is somewhere between 3 and 8. So actually, the MCE is divided by 2/3, and then it's divided by something like maybe even as big as 8 before we design the building for those forces, with the assumption that it has the capacity under very rare ground motions to still stand up when it sees that thing that is 1/5 times 8 times the design coefficient bigger. And we have reason to believe that's actually true most of the time. But these are all the formulas that the engineers are using that are in Chapter 11, Section 11.4. Another cartoon to help explain some of the ideas. This is from Project 97, so back up in time 10 years and say, what were we thinking back then? What were we thinking back then? What this plot says is on the vertical axis, you're looking at a particular intensity parameter. This happens to be 1 second spectral acceleration. And the cartoon says, conceptually, if you're moving from areas of very high hazard on the left to areas of very low hazard on the right, then things have to get less as you go across the screen. Imagine you're kind of walking from the San Andreas Fault in California toward New York, and there's no faults in between. What it shows and compares are various perspectives on this parameter from different codes. The blue, which you see a zigzaggy chain link fence, that's the old UBC zones. Zone 4 is around 0.4, and then it drops off 0.3, 0.2, 1.5, and 1 as you proceed into lower hazard areas. What we said in 97 is that we need to use contours. We need to use a probabilistic calculation that will essentially replace that zone with a set of contours. And what that is the red, upper reddish looking curve there. And we wanted to make that curve have a rare enough occurrence to capture these rare events in the central and eastern U.S. So we were looking at, as I said, all of 15 minutes, in using something around 2% in 50 years to capture rare events in the lower hazard areas. And that's what that curve kind of does. But you see what happens to the curve in the areas of very high hazard next to active faults. It goes through the roof. And we said in those areas, there's no reason to use a 2% in 50-year hazard, which is a 2,500-year return period, for events which happen every 300 years. It doesn't make any sense. If it happens every 300 years, maybe we can just take a conservative view of the big earthquake and use it for design, and that's the deterministic answer. And in fact, it was very, very much like what we had in the UBC in terms of near-fault coefficients. That's that little dashed line. So what you see on the lower kind of orangish line, yellow orangish line, is a deterministic calculation based on 1.5 times the median, probabilistic at 2% in 50 years. All these things are taken 2/3, so it's in terms of design coefficients. So we define the probabilistic domain as this region of 2% in 50-year ground motions, a deterministic limit based on 1.5 times the median of the maximum possible earthquake, and some little plateau to get between the two. This is all what was in place 10 years ago, current codes. Project 07, what do? We went back and said, let's revisit the 2% in 50-year assumption. Maybe it should be something else. We came up with 1% in 50-year risk. I'll talk more about that later. We said the 1.5 in the near source region. Gee, it's supposed to be 1 sigma, but maybe it's not 1 sigma. Maybe it should really be 1 sigma. How much is 1 sigma? Turns out 1 sigma is more like 1.8. So the new code will be based on 1.8. We don't want to underestimate this thing in the near source region. And then we also revisited this question of 1% spectral acceleration. What are we talking about? Codes had actually not defined in the codes what parameter we were really talking about in terms of that. And we said, well, if we want to get it right and get our probabilities right, it has to be the maximum direction. And I'll explain more about what that is. So those are the 3 basic changes conceptually shown on this cartoon. A little, again, what was this issue? Why did we go to such an extreme return period last time? If you see, this is a set of hazard functions for selected cities throughout the United States. They're outdated hazard functions, but it's the same story. This is from 2003. If we slice these hazard functions where we had traditionally sliced them in the Uniform Building Code 20 years ago, we'd be slicing a 10% and 50-year hazard level, which would be around a 500-year earthquake. We moved that down to 2% in 50 years this last cycle. We're now discussing how to bring that back up some maybe. Why did we do that? If we're comparing Los Angeles in a design sense, comparing Los Angeles with Memphis, we would see that Los Angeles sliced at 10% in 50 years would be about 40% G, which is not unreasonable. Memphis would be 6% G, which is pretty unreasonable since it's on the edge of the New Madrid zone. And that's because of the shape of the hazard function, the slope of the hazard function. If we go to a more extreme return period and take 2/3 of it, we see that Los Angeles is about the same. But because of the slope of these functions, Memphis has now moved up to 25% G, a much more reasonable estimate of the big event in Memphis, which may occur less frequently than California, but we would certainly miss it with a 10% and 50-year function. So our thinking was we needed to move down to a more extreme view of return period to capture these events for places like Memphis. And that led to this map last cycle. Now, that's fine, uniform hazard, 2% in 50 years with all the rules I described. But maybe, that's really not what we're trying to do, because getting uniform hazard is not what the code's trying to do. Getting uniform protection is what the code's trying to do. And it was recognized all the way back in ATC 3, which is the forerunner of the NEHRP provisions, that uniform hazard does not mean uniform risk. It was just the best we could do at that time. And now what we're saying is we can do better. We can actually pick ground motions on the basis of achieving more uniform risk in terms of avoiding structural collapse. So that's the big change, moving from hazard to risk. Doesn't actually change the numbers that much, but conceptually it's a big change. So if we design for 2% in 50 years, we don't necessarily get uniform collapse. We have decided that we can aim at a risk goal, and the absolute risk goal we're aiming at is a collapse risk objective of 1% collapse risk, 1% of the buildings collapsing, if you will, in a 50-year period. And we had big debates about whether it should be 1. Now, we believe in round numbers, so there's no 1.1s in this game. There might be a 1.5, and there might be a half, and there might be a 2, but there's no 1.1s. The precision just isn't like that. But this seems like a very reasonable objective, which is very consistent with having a 2% and 50-year hazard for a lot of regions. But to get there, we also have to have a conditional objective. We have to know what we think will happen if there is the MCE. What do we think is acceptable if this rare big earthquake occurs? What fraction of the buildings would be deemed, if they collapse, would still be deemed acceptable? And that conditional probability, given the MCE, is 10%. So two major assumptions in these new ground motions. First, 1% in 50-year absolute risk, and a conditional probability, given the MCE occurs, of only 10% collapse rate. That one causes a lot of heartburn because that's a pretty big number, but it's a very, very, very rare earthquake. So I'm going to show a couple things that talk about how we get to these answers, and Nico is then going to, after you get really confused, Nico's going to explain it to you. So don't worry. To do this, we have to find a way of combining the hazard functions, I showed you those before, with some fragility curve that represents the structure's performance to get this calculation of 1% risk. It's done through what's called a risk interval, and it's fancy stuff, but that's why we got the USGS there working for us. Point is, I want to talk about this so-called fragility curve, the collapse fragility curve, because when the first time structural engineers hear this, they say structures don't have the same fragility curve. All the structures are different, and that's true. But for the sake of this calculation, we assume a generic curve. We assume that all the structures that are being designed using these ground motions are achieving that 10% risk goal. So for the engineers in the group, we're not saying that the buildings will all perform the same. We're saying we hope they would do this, and if they do this, then we know how to make the adjustment for the ground motions. Somebody else is going to have to fix the other side of the equation, which is the R factors, to achieve that uniform fragility for all the structures. So this is the function of the risk calculation. I mentioned this because I wanted to say that part and parcel of this calculation is this assumption that given the MCE, you have no more than a 10% chance to collapse. We have reasons to believe from various projects like ATC 63 that this is a reasonable assumption, and it is consistent with the commentary of the NEHRP provisions, which says given a MCE, we should have a relatively small probability, not zero, but a relatively small probability of collapse. Let me move on to ground motion intensity, because just understanding the terms is difficult, so let me show some pictures to help understand what we're talking about here. The NGA functions, like most attenuation functions, are based on a geometric mean measure of intensity or some version of geometric mean. We chose a different definition for the purposes of putting ground motions into codes. Let me explain what those two things are because they're not necessarily clear to everybody. What you're looking at here is the response, looking down from above. Imagine you're looking down from above at a lollipop that can move in the X, Y horizontal domain. So you're looking at the response of a lollipop to a given earthquake record. You'll notice it has some peaks. It has a lot of elliptical motions. They tend to do that. Moves all over the place. So we have a fault normal, fault. In this case, the record has been oriented in a fault normal, fault parallel direction, showing not necessarily that it's 100% maximum with one direction or the other. The box that recorded this ground motion was put on the ground, the box, the instrument. If you put it one way on the ground or another way on the ground, you get different answers, obviously, in the two X, Y values. They will change depending on how the box is on the ground. The squiggle does not change. The X, Y axes on the squiggle can be rotated, but the actual circles, the squiggles, they don't change. Okay, so the first thing that was a problem with a lot of this stuff is period dependence, is orientation of the box dependency. The other one is it becomes also very period dependent. We get different answers depending on whether you're at short periods or long periods. The geometric mean is the square root of one component, spectral response of one component, times the spectral response of the other component. And this varies, as I said, with the XY orientation of the traces, the way they were recorded. So it's got some record orientation issues. The NGAs used a very fancy way of calculating the geometric mean to help remove that orientation issue. Okay, so it's kind of resolved some of that. Turns out it's about the same answer as the geometric mean. So the good news is it's bad news it's complex. Good news is it doesn't matter too much. We chose a different way, which says we want to go look at the maximum as our definition for code design. I'll tell you why, but that's the red dot over here instead of the product of these other two. So we're looking at the resultant in the horizontal domain. What am I talking about here? Here's a trace from Coachella. It's a very strong earthquake record from the Coachella earthquake in '99 in Turkey. To calculate a response spectrum, we run this record through little lollipops of all different periods. Okay, and these lollipops have only one direction of response, but you could run them simultaneously, get that combined response. And if we did this, ran this record, these records, the two components, independently through these two lollipops at 1 second, one of many periods, then we get these traces. This is the response of a 1 second system to a linear elastic response of a 1 second system to the Coachella record. And then we would say, to calculate the geometric mean, we would go and find the peak in the component 1 direction and find the peak in component 2 direction wherever they occur during that response of that record. And then we'd multiply those together, and then we take the square root. That's the geometric mean, definition of the geometric mean. As an engineer, I don't know what that means because they don't occur at the same point in time. So it has some statistical nicety, but it doesn't necessarily have engineering significance. So if you do that, and you can compare the response spectra of the geometric mean with the response spectra of one component versus the other, or that little faint line, a little tiny faint line is the arithmetic mean. So if you just, instead of multiplying the two numbers together and taking the square root, if you just add them together and divide by 2, that would be the little faint line there, which is almost the same answer. But you can see sometimes this geometric mean is about the same as the calculation of either spectrum when the two spectra are about the same, because when you multiply x times y and x equals x, the square root of that is x. So it converges on the spectra when the spectra are similar, and it diverges when they're not. The maximum direction ideas, to go back to that look into the horizontal plane, go back to the notion of response spectra. The notion of response spectra is I want to find the maximum response. I don't care when it occurred during the record, just tell me what the maximum response is. Only this time, use a two-directional or a bidirectional horizontal response of that one period structure and simply look for the resultant. That's the maximum direction. So it's really a response spectrum idea applied in the horizontal plane. Turns out it doesn't change too much in this case. So here's a comparison of that, the resultant in the horizontal plane, versus the geometric mean. Sometimes they're very close together. Sometimes they're not so close together. If we do some statistics on it, you can find that there are patterns to how much they vary. And that's important because when we wanted to use the maximum direction, we had to have some rules about how to convert the equations that are based on the geometric mean into the maximum direction. And you can see that at short periods, it's about 11% difference and about 18% in this particular record. In fact, to do that, we had a study that was done by Andrew Whittaker and Nan Wang, his student at the time, and Nico, to take a look at how these trends occur between this maximum direction and the geometric mean. And we found that it's about 1.1 at short periods, about 1.3 at 1 second. And in terms of looking at 84th percentile response, which we need for the deterministic, it's about 1.8 difference. That's where we got that 1.8 number that went into in lieu of the 1.5 in the previous code. So we did some homework to figure out what these numbers ought to be. These were for near field records because that was our focus at the time. There's been some other studies by other folks that would indicate that these are the similar sort of numbers would occur in other regions than near field. So why do we care? Why do engineers care? Building design considerations. We care because we design one building direction at a time. And we got to get it right, understanding that the earthquake will apply loads in both directions to the building. And if we take a set of records and we apply them, each record, to a one-directional analysis, and we ask ourselves, how much bigger do I make them before I get half the records to drop the building? As opposed to taking the same set of records with their XY orientations to a three-dimensional model and scaling them up, we find that the collapse point is different. And in fact, records along a single axis are approximately 20% less likely to collapse a structure than when the same records are applied in a bidirectional sense. So because we're doing unidirectional analysis and design, we want to make sure we get it right. another way of thinking about it is if a building collapses in the X direction, but it doesn't have any damage in the Y direction, do you average or is it a collapse? You don't average collapse. You can't average. You got to integrate if you're a probabilist. You got to integrate with the Boolean logic to the answer that you need. And the answer is collapse. So you can't start averaging too soon because any collapse in any direction is a collapse. So anyway, there's some studies that would show this 20% rule, which is not unlike this 1.1 and 1.3 type numbers, makes sense. And why is that? As I just said, buildings can collapse in whatever the strongest direction of shaking is going to find the first point of collapse for the building. And it tends to govern. So we said let's use maximum direction, base it on this 2-degree or this lollipop with complete freedom in the horizontal direction. It's readily converted from the existing geometric mean intensity. Ron's telling me to move along. And it's appropriate for ELF, or equivalent lateral force design, but it is not appropriate for scaling records. When you're actually going to apply records to a building simultaneously, you don't take the maximum in this and then say it's the maximum in this direction too. There's only one maximum. So we've made some other adjustments in the code for time history analysis. Instead of scaling to a 1.3, we now scale to 1. So this 30% adjustment that's in there for ELF comes back out when you're doing time history analysis. And just to compare, here's that same record I showed you. Here's a comparison of the record with the maximum direction, that's the black, the geometric mean, which is red, the prediction from the NGA. I looked at this, I said, oh my gosh, NGA, it's low. Oh my gosh, I said, but you see, every record's different. Every record's different. It turns out that this record is above the average. So I went back and I said, let's take all the records in a class of records that I'm interested in. All the big magnitudes, all the strike slip records, all these CD soil types, which is almost all of them, within, say, 20 kilometers of the fault. So all the records that are most important to me as an engineer. Out of all the thousands of records in the database, there's 11. Only 11 that match that. The Seattle fault, the one we're trying to characterize here, 11 records, let's say. Now, that's good. The good news, though, is there used to be 4. Before Turkey, there was 4. So we're up to 11. But the point is, there's only 11 out of thousands that really matter a lot to drive this. But if I take those 11, I predict for each of those 11 what they're supposed to do, and I take the average and compare that prediction with the average of these guys' spectra, it turns out that it looks very good. That is, the blue curve, which is a little zigzaggy, is the average of the actual spectra of these 11 records, and the red line that's going through it is the average of the predictions of these. So the NGA is doing a very good job of emulating the data that's in the database for these 11 records. So that's the good news, is they work really good. The bad news, which is not anybody's fault, we just haven't been around long enough with enough instruments, is we still need a lot more data, because after we have the next big strike slip event, and we get 50 data points, and it goes from 11 to 61 data, I'm just going to bet the average changes. That these statistics are going to change. So remember, we just don't have all the data we need yet. And guys in codes, like myself, code committees, we have to be aware of that. The big ones that really dominate our thinking have a limited number of data to support where we are at this time. Okay, there's a ground motion map of the US. Let's take a look, before I run out of time here, let's take a look at 34 cities. You know, when we come forward with these committees, no matter what you say in the theory, you can say anything you want in theory, the first thing out of the mouth of anybody in the room is, yeah, but how much of the number is going to change? And you go, I don't know yet. And you go, yeah. So we sat down, took 34 cities, spread them out through the United States, and with the help of Nico and the USGS, developed what the numbers were going to be for those cities and could compare them with the current code with the future proposals. And we tried to pick areas of major interest. And when we put together average, we tried to weight the averages by the population exposure. So if there was 2 numbers to be added together, an average to find out what the average effect is, we tried to normalize that, if you will, by the exposure, the population in the regions. And because we don't know actual site conditions, all these are based on an assumed site class D, not the nominal site class D situation, because we actually don't know the sites for these 34 cities. Okay, so here's a Google map of the US, the little thumbtacks are the cities. We spent more time in the west than the east, but we did hit Chicago and some of the big ones in the east, New York and Charleston, Memphis, St. Louis. Here's an overlay of that probabilistic map I showed you, kind of give you a sense for how it's going. Let's focus on the Pacific Northwest. where we had thumbtacks at Everett, Seattle, Tacoma, and Portland, which represents, frankly, the counties that those cities are in represents about half of the populations of Oregon and Washington. And this is the statistics. We need these lat longs to actually go into the USGS database to get the numbers. Here we are in a little closer view. You are here. That's where you are right there, somewhere in Belleville. I think I'm pointing at this hotel. The site that we are going to compare values for is the Seattle City site over here. At the time we did this, the USGS only had a grid of points, so we had to pick a thumbtack that was nearest one of the grid points in the database, and this was the best one for Seattle. It's about 2 to 8 kilometers from the Seattle fault zone, so you're pretty close to the Seattle fault zone. You have the deep subduction event also as a contributor hazard, but very much also a local event. Just some numbers for you. We haven't got a lot of time on this, but if you look at the top row, which is Seattle, it's in green. It's good. It's in green. If you go to the far right-hand side, it says 1%. That means that this site over in Seattle is controlled by probabilistic ground motions, and the ground motions are based on the risk goal of 1% and 50-year hazard. If we go back to the hazard function and say, what is the return period of the ground motions that give us 1% risk? Turns out it's about 2,000 years. We tend to see this, but the 1% risk in a lot of the regions of the US turns out to be more like a 2,000-year return period. The other numbers on that line are the individual contributions from deterministic and probabilistic and risk coefficients that you would find in the NEHRP provisions. We roll them all together into ASCE 7, so you don't see all those pieces, but you can get those out of the NEHRP provisions. When you roll them all together and you take 2/3 of the MCE, you get 0.53 G at 1 second for the design coefficient. How does that compare with the previous version of ASCE 7? Again, the top row. The new code will have 53%. Used to be 49%, used to be 56%. The UBC thought it was 54%. In 97 and 94, the UBC thought it should be 56%. By and large, it's the same number. I think you're going to see that that trend is it's by and large about the same number. If we average all of the Pacific Northwest, the average of the counties that we looked at in the Pacific Northwest would give us about 49% G compared to 44 previously, compared to 46, compared to 54 for the UBC. So actually, you've been using the UBC for design in this area, and in fact, it's lower than what people have been using traditionally by a little bit. Same story for short period accelerations, very similar numbers, more or less the same, in fact, a little bit lower than before at short periods. If we look across the whole United States, we're looking at regions, Southern California, Northern California, Pacific Northwest, Intermountain, Central and Eastern US. We can make the same sort of comparisons. I won't go through them all, but if we were average the entire United States, weighted by population, we would say the average design coefficient at short periods is 72% G. Used to be 73, used to be 72. So it's about the same. We like to think we don't yo-yo a lot in codes. If your particular area goes up or your particular area goes down, it's because of the underlying changes to the seismicity, hazard, understanding of those things. But on average, the code should not be changing the parameter too much. Bar chart of the same. If we look at 1 second response, similar story, 40% compared to 38 and 39. Not a lot of change. Same thing. So let me just close. It's an ongoing process. We're through NEHRP. We're almost through. I think we're through ASCE 7, but it is still being put forward for consideration in the model building codes, which means the IBC. So it's not done with respect to the IBC yet. A word of caution. All these ideas that I've been talking about come as a package for code usage. They come as a package. You can't cherry pick. You can't say, oh, I'm going to use the NGAs. They really lower 1 second response and not use the other stuff. No cherry picking for designing buildings. Now, all this is very confusing, but the USGS has a wonderful website, and there's GIS tools like Google, which you've seen. So, in fact, the delivery system for engineers is going to be through a web-based software. So you type in your building's lat long, which you can find from Google in 2 seconds, and you type in your lat long, and these coefficients for designing buildings will come back to you. And so all this good stuff is just background, but when you go to use it, it's a lot simpler. So with that, I'll close, and thank you very much.